Continuing on, what I was saying was p-value tells me the probability that the sample would have shown the null hypothesis, that there was no difference. However, there may be errors with that significant statement, right? The errors of significance of that calculation. There's type 1 versus type 2 errors. Type 1 says the results, it's a false positive in that sense. There, you got a difference, right? There's a difference between people who want to take GPS versus no GPS, but we had reached the wrong conclusion, meaning that if I were to expand that study to a larger population of pilots, there might have been no significant difference between the two, right? Our sample just happened to show us a positive difference. Whereas a type 2 error says that the results said that there was no significance, but in reality, there is a significance in the population, which is a little bit more dangerous in that sense if you think about it. Think about um, um, a medical trial, right? And you're trying to see if there's no, what's the word I'm looking for? There's no adverse effects. There's no side effects from your medicine that you're giving out or you're testing, right? A type 2 error is a little bit more dangerous to get. If you're saying, oh, the sample size that I have, there's no side effects. We can mass produce this and give this to everyone. And so that's a problem because in reality, maybe we didn't really measure enough people to give us a strong p-value or a strong significance statement, in terms of the statistical analysis to see if there was a significant difference. And so that's going to be a problem because if I mass produce this, the population who uses this may have a significant reaction to that medicine, right? So what we're trying to do is minimize type 2 error by making sure we have the right power for the study. How do we do power? Well, we have to make sure we have enough of a sample size that will be significant or correct, correct for the statistical test that we're going to do. So I briefly talked about this concept of a software tool called gpower to calculate for it. You can do it mathematically by hand, but let's use software, right? What gpower does is says, okay, what is the minimum sample size that you need to have to give a strong power to say, a higher chance that you've got a better result or a lower chance of having a type 2 error, basically, right? And so we are doing a type of t-test called the Wilcoxon matched pairs test. So we're going to click that. We're testing an a priori, right? A priori with a normal distribution. We're keeping it pretty simple. Our probability, our alpha, our p-value that we want is something less than 0.05. So that's our decision. Alpha is in statistics, alpha is our power, is our p-value that we want to achieve in order to say that was statistically significant or not. Power is defined by 1 minus beta, or the error probability of beta, meaning the percentage that we're willing to say that our significance needs to happen for that sample size. So in most of the cases we say it's got to be 20% chance that our significant value is wrong. Our significant test, our statistical test is wrong, which 1 minus 0.2 or 1 minus 20% is 0.8. So we want a power of 0.8, 80%. So that's our typical. You can have your power higher. So if we put a higher value, that's going to give us a different value. So let's take a look at that. With this setup, our power analysis, if we say we want a power of 0.08, meaning 1 minus 20% chance of being of getting a type 2 error. So we're trying to get a stronger test, 0.8 value of a test. Our sample size needs to be 28. Okay. If we want a stronger power, let's say we want it to be 0.9 with still a alpha of 0.05, we need a larger sample size, 38 people for the study, in order for us to say we had power. We have a lower chance or lower probability of having a type 2 error. If we make this 0.01, so a lower probability that the null hypothesis would show up in our study, and a strong power. Take a look at our sample size. So basically what that says is the higher the sample size, if I've got 58 or more, I can say that, you know, my alpha p-value can be 0.01 or lower, and if my power is 0.9, that's a strong power, right? Strong study. That means my study's significance is more important. That means that's saying, hey, there's really a statistical significant difference between the two. We never say it proves something, but there's a significant difference that there's people that are most of the population. If I were to take this to the population of pilots, all pilots in the U.S., the willingness to fly, I can predict that the willingness to fly will be higher with those who want the GPS than with the GPS than those who don't want the GPS, right? Or don't have a GPS, right? So you could do the same thing with your study. So I want you to be able to do the Excel side of things from Google Forms, the analysis with respect to SPSS, and then using G-Power to figure out or determine what your sample size is. And most of you, let's not worry too much about this per se, because we're going to have some limitations for the sample size. So as long as we're aware of this, I all want you to have a p-value of 0.05 or less than 0.05 to be statistically significant. So we'll keep that at 0.05. And if any of you are doing a Wilcoxon test, let's just say anything above 28 as a sample size is pretty good for power. All right. So what I've done is I've got a couple different studies that samples this. There's two data sets that I want you to give a shot to set it up kind of like this, make a graph and show the difference between two groups, and analyze that. So I've got a couple here that I'll probably go over with you all and go from there, or send it out on Blackboard.